All right, let's jump right in. We're going to talk about how artificial intelligence is starting to completely revolutionize one of the most complex fields of medicine, cardiology. And look, this isn't some far off sci fi concept anymore. This is happening right now. It's the new frontier. But let's start with a really simple question. You've heard it a million times, right? Normal blood pressure is 120 over 80. But what if I told you that normal number might not be normal at all for you? This one idea, it really gets to the core of a massive shift happening in healthcare. You see, for decades, medicine has pretty much run on what we can call the normal delusion. That 120/80 number, it isn't some magic universal constant. It's just an average, taken from studying tons and tons of people. But your body has its own personal normal, and it could be totally different, and you could be completely healthy. And this slide just lays it out perfectly. We're moving away from this old idea of population-based medicine, which, let's be honest, is kind of like a one-size-fits-all t-shirt. It fits, sort of. And we're moving toward personalized medicine, which is like getting a custom tailored suit. It's made just for you. And the tool that's making this huge leap possible, you guessed it, it's AI. So you can think of AI here as this genie in a box. It's this unbelievably powerful tool that can just comb through mountains of data, see patterns a human doctor could never spot, and give us these life-changing insights. But like with any genie, there's always a catch. And that catch, it all comes down to a single word: trust. I mean, how can doctors trust what comes out of a black box? If an AI says a patient is at high risk for a heart attack but can't explain why, its own thinking is so complex, even its creators don't fully get it, how can a doctor confidently change someone's treatment based on that? They can't. Without understanding the why, we can never really truly rely on it. So, okay, let's try to crack open that black box a little bit. If we're going to build trust, we have to first understand, how does this genie even learn in the first place? Well, it mostly comes down to two main approaches. The engine that makes this all go is something called machine learning, and it's kind of the opposite of traditional programming. Instead of giving a computer a huge list of rigid if this, then that rules, we just feed it a ton of data and basically say, hey, you figure out the patterns. And that learning, it happens in two main styles. Over on the left, we've got supervised learning. The slide calls it learning with an answer key, which is perfect. Imagine we give the AI thousands of patient records that we've already labeled healthy or unhealthy. The AI studies them and learns to tell the difference. But then on the right, you have unsupervised learning. This is where we just dump a giant, messy pile of unlabeled data on the AI and say, go find something interesting. The AI starts grouping things on its own, and sometimes it finds connections that we humans had totally missed before. Okay, so if machine learning is the engine, what's the fuel? What kind of data is this AI actually using to get so smart about the human heart? Well, it turns out there are four main ingredients, or what we can call the four pillars of data. And here they are. When you put these four things together, you get this incredibly sharp, high-definition picture of a person's heart health. We're talking about images like CT scans, electrical signals from your heart, that continuous data from things like your smartwatch, and finally, the most fundamental data there is, your genetic code. Let's just quickly break each one down. First up, images. So think CT scans, echocardiograms, that sort of thing. A human radiologist is amazing, right? But an AI can look at every single pixel in that image. It can spot tiny textures and patterns that are literally invisible to the human eye, finding potential problems with an accuracy that can get over 95%. It's incredible. Second, we've got signals, and the classic example here is an ECG. To us, it's that familiar up and down squiggle, but to an AI, that squiggle is a rich, complex wave packed with information. The AI can analyze every tiny little fluctuation, every millisecond, and find these subtle clues that might predict a future problem long before a doctor would ever see it. Number 3 is continuous data. And this is the big revolution from wearables like smartwatches. Think about it. Instead of one blood pressure reading in a doctor's office once a year, the AI gets a 24/7 live stream of your heart rate, your activity, your sleep. This lets medicine make a huge shift from just reacting to problems to actually predicting them before they ever happen. And that brings us to the fourth pillar, and this one is probably the most profound. It's your genetics. Your unique DNA holds the blueprint for your health, including your inherited risks for heart conditions. And just as important, it can predict how you, specifically, will respond to certain drugs. This right here, this is the foundation of truly personal medicine. So, We have this powerful genie learning from these four incredible pillars of data. It sounds amazing, right? But here's the catch. This genie has a critical and frankly dangerous flaw. It's only as good and only as fair as the data we decide to feed it. There's this old classic saying in computer science that just nails the problem perfectly. Garbage in, garbage out. If we train our AI on data that's flawed, or incomplete, or biased, well, then the AI's decisions are going to be flawed, incomplete, and biased. And in medicine, that can have life or death consequences. So where does this bias even come from? Well, here are a few of the big ones. First, there's population bias. If you train an AI mostly on data from, say, men of European ancestry, how accurate is it going to be for a woman of Asian ancestry? Not very. Then you've got sampling bias. Imagine training an AI on heart data that was only collected when people were sitting down. That model would be clueless about how a heart works during exercise. And finally, there's model bias, which is basically using the wrong tool for the job. It just shows why having really diverse, global data is absolutely critical to get this right. Okay, so that brings us back to the biggest challenge of all. How do we build a genie that is not only powerful, but also trustworthy, transparent, and fair? Well, the ultimate answer, the real holy grail of this entire field, is an idea called the digital twin. The goal here is to transform that black box into what the experts call explainable AI. You know, it's like in a math class. It's not enough to just write down the final answer. You have to show your work. The AI needs to be able to turn to a doctor and say, I think this patient is at risk, and here are these specific data points from their scans, their ECG, and their genes that led me to that conclusion. And this is where it all leads. This is the ultimate vision, the digital twin. Just imagine a perfect, dynamic, digital copy of your entire cardiovascular system, living and breathing inside a computer. It's built by feeding all four pillars of your unique health data into the system. It wouldn't just be like you. In a way, it would digitally be you. Just stop and think about the possibilities here. Before a doctor ever gives you a new medication, they could test it on your digital twin first. They could see exactly how your specific body will react. They could find the absolute perfect dose. They could check for any weird side effects, all inside a simulation, with zero risk to the real you. Forget a tailored suit. This is medicine tailored down to your very DNA. What is absolutely clear is that we are standing right at the beginning of a medical revolution. By taking our most personal data and combining it with AI that is smart and, this is the key, explainable, we are building a future of healthcare that is truly, deeply personal. And it leaves us with one heck of a final question to think about. Could this digital version of you one day see a heart attack coming, long before it ever happens?